Okay, so what we're going to do today, there probably won't be so many examples today because I'm going to dissect some of the important properties and determinants that you're going to need, some of the consequences, why we care about it. So, but you all remember my example from last time, right? 25 by 25 matrix. If you do a cofactor expansion, take 500,000 years, right? Work it out. 30 by 30, it's like 8 trillion years, right? This technique that I'm going to show you will reduce the time from 500,000 years for 25 by 20 to a few thousandths of a second, right? So it's better. Actually, for human beings, it doesn't help quite that much, but for computers, it's quite a bit. So first, I need to follow here. And this theorem, somebody was asking last time about row reduction, right? I mean, can you row reduce these things? And the answer is yes. You can row reduce matrices. See, once again, here we are with the row reduction, right? It shows up over and over again. You can row reduce matrices to find determinants because there is a certain amount of control on what row reduction actually does to matrices. And let me tell you this. I'm not going to prove this theorem formally, but I'm going to show you why it works. So suppose you have a square matrix. Number one, if a multiple of a row of A is added to a different row to form B. So this is like one of our first matrix operations. You take a multiple of one row and add it to a different row. So suppose you take A, take 7 times the third row and add it to the 20th row to make B, the determinant does not change. And that's really the big one. The other ones are a little bit easier. This one's, you have to think about this a little bit. If B is obtained from A by swapping 2 rows, what do you suppose the relationship is between the determinants of A and B? I want to guess that.
Would it be like the determinant of B would be the negative of the determinant of A?
That is correct. So if you swap 2 rows and only 2 rows, it changes the sign of the determinant. How about this one? If B is obtained from A by multiplying a row of A by the number K, what's the relationship now? That is correct. By the way, with our matrix operations, what was the thing? So what can you do? You can add a multiple of one row to another row, you can swap 2 rows, or you can multiply a row by a number. And what do we say about the number? Yeah, for that particular one, we always say the number is not 0. Actually, for this one, it doesn't make a difference whether K is 0 or not. Because this is true if K is. This is true if K is not 0, and it's also true if K is 0, right? Because if K is 0, then what's true about B? If I take A and I multiply 0 times one of the rows, don't I get a row of zeros in B? And if B has a row of zeros, its determinant has to be 0, right? Because it can't have any pivot columns, or you could, how about this? You can expand across the row that has all zeros in it, and you will get 0 determinant, right? That's another easy way to do that. Okay, any questions on that? Okay, the first thing I want to do is I want to kind of demonstrate why this is true. Like I said, I'm not going to do anything super formal. I just want to give you an idea of why this makes sense. First of all, I'm gonna probably come to this one last. Why does swapping two rows do things? I'm just going to do a 3x3 example. Suppose I have this A, B, C. D, W. Can somebody explain why swapping two rows should change the sign? So let's let B be B, W, A, B, C, X, Y, Z. I can expand this across the first column, right? And I get A times this determinant, negative B times the determinant off the sides, and C times, right? Everybody agree with that? What happens if I expand B around the middle row? I get A times, don't I get the same determinant here? BZ minus YW, and then B, negative B times UZ minus XW, and then finally C times UY minus VX. Don't I get the same thing? Doesn't it seem like I get the same thing? But it's actually, why does the sign change here? When I expand across the first column, it is A times determinant of BZ YW minus B times determinant of UWXC plus C times determinant of UVXY, correct? And my question was, why is it the same here? What happens if I expand across this column? First, I'm going to have A times this determinant, UW or VW, XZ, or this row is called YZ. Goodness, isn't that the same? Looks like I'm going to get the same thing. It doesn't look like change the sign. Or did I forget something? Is the first term when I expand across the second column, what can you say about the A there? It needs to be negative because this is, remember that -1 to the row plus column? The row plus column here is 2 plus 1, which is 3. So this is actually negative, right? And then positive, negative. So this actually goes to the same thing. When you do it here, it's negative, positive, negative, because you've moved one row down, right? And but you might criticize me again and say, but Jim, what if you did this? What if you swapped what if you, let's see if I do that right. Yeah, so what if you swapped, these two here? Right? Because now the signs are the same. Everybody agree? It's gonna be A permanent, whatever's left over, YZ, BW minus B, determinant, whatever, XZ, UW, plus C determinant, XY, UW. Goodness gracious. Yeah, this can be right. Let's see, A, that's a determinant, Y, T, C, W, right? Almost forget this determinant. This is B. This one all the time is supposed to be DW, Y, Z. So, why is this the opposite sign to this right here?
The determinant inside is flipped.
We flipped all the determinants aside, right? And so this persists all the way up, right? It should be the minus sign when we switch these rows by. Everybody see that? This is essentially why it worked. And how do you go from there? You go by induction. How many of you have ever heard of induction? And not in a physics class, right? Mathematical induction, what that means is it's a stairway to heaven, right? So what you do in mathematical induction is you prove that it's true at the bottom, and then you prove that if you've ever got a step on the ladder, you've got a next step, right? So you show the first case is true, and then you show if you've got any case, you've got the next case, and now you get your stairway to heaven, because you've already shown that you've got the first rung on the ladder. But you know that if you have any rung, you've got the next rung. So now you've got the second. Well, now you got the second. If you have any rung, you got the next one. So now you got the third, and it goes on forever. And this is basically the way you build these here. And this is why I swap. Is everybody pretty comfortable with the fact that swap can go is going to change sign of the term? The easiest one, I think, is this one right here. Let's do this one. What happens if I multiply a row by K? And I'll just multiply the top row by K, because I've already shown that swapping only changes a sign, so I might as well multiply the top row. Can anybody explain why this is K times the determinant? The original matrix is A times this determinant, B times this determinant, C times this determinant. You just do the same thing, and now you've got a K from there, right? It's got a common factor of K in it, so it works out. Everybody okay? So that is basically a justification. This, the important one, I've always thought, is what about this business about? This is the one that's not clear. Is it? So if I do something like, what if I take the middle row times 23 and add it to the top row? It's not clear why that. It seems like that might change the determinant, doesn't it? I mean, it does to me. I don't know why. Leave that alone, but let's see what happens here. Now let's take, I don't know, K times this and add it to the top row. Now, why does that have the same determinant as the original? Well, it's basically because of linearity in the columns above. Let's work this out. This is A plus KU. That's determinant of U, VW minus B plus KD times determinant of UW XC. Plus C plus KW comes the determinant of last bit, which is UV XY. Everybody okay with that? Now notice, I've got something plus something times mess, something plus something times mess, something plus something times mess, not that parentheses. So can I multiply with parentheses, right? I can do that. So I could write this as A, determinant BWYZ minus B, determinant UWXC plus C, determinant UVXY. And then I've got a KU determinant minus KV determinant plus KW. Everybody okay with that? Now, can somebody tell me what's another name for this? That first line? Well, I'm just gonna try to take this backwards. The first line for this is A times this determinant minus B times this determinant plus C times this determinant. So that's just the determinant of the 3x3 matrix. This one. Everybody agree with that? What about the second line? Can you interpret that as a single determinant? Well, look, you got the same little matrices right here. So I bet the second and third rows are the same. What goes in the top row?
AU kid.
Everybody agree with that? See how I reverse engineered that? Now, second determinant is C. But anybody tell me why?
It's literally dependent.
That is correct. How do you tell if a determinant is zero? It has less than, this is a 3x3, it will have less than 3 pivot columns. Everybody agree with that? If I multiply this by negative K and add it here, I've got a row of zeros. So it has to have less than 3 pivot columns for sure. Everybody agree with that? If it's got less than 3 pivot columns, it has to have determinant zero. Everybody cool with that? So this is zero because less than or equal to 2 pivot columns. And so our conclusion is the determinant of this thing is equal to the original determinant, and that's why that works. Everybody okay? Okay, so that's a little bit up under the hood, so we know kind of why that works now. And I guess the big other thing I can show you is the product and the transpose. Okay, so here's an observation. Questions. Actually, let me do kind of a numerical example, kind of catch our breaths here. And I'm gonna do this example, then I'm gonna dig a theory. I want to find the determinant of 4507 minus 1, 2, 2, 3, 6, 2.14 and 2.004. Well, I'm gonna do some row operations here and try to keep track of what I'm doing. The 2 is obnoxious here, so I'm gonna pull this 2 out. This is 2. Four, 507, 1, 2, 1, 2, 3, 6, 1, 4, 1, 0, 0. If I do that, if I agree. Now I can swap up. I'll do that. But I have to do something. What I have to do here. I gotta change the sign though, because didn't I swap 2 rows? So this is -2. All right. Now I'm gonna do some row reduction, right? And I dig on the, or I'm sorry, row replacement. That's what I mean to say. I'm gonna replace it, and I dig the row replacement because I never changed the sign of the determinant. So I am going to all at once. I've got 1002. I'm gonna use this 1 to take this out, straight up add. Right, okay with that? So that's 212. Thank you. Yes, 214. That could have potentially burned me later. Okay, multiply by -3, take this 3 out. That's gonna be 6, 1, -2. And finally by -4 to take this one out. Let's see, -4 is -8 and 7 is -1. Now at this point, we could expand about this column, right? That would be a good thing to do, right? But I'm gonna do some more row reduction now, right? So feel free to like do whatever you want. Like at this point, I might say, you know, I like 3x3s and 50-foot with them. I'm just gonna bag it and expand about this column, right? But I'm gonna go ahead, I'm gonna use this 2 to take these guys out. By the way, can somebody tell me about something about this determinant that should be true? So is it possible for me to get like, I don't know, 3/7 as a determinant? Notice this matrix has all integers in it, right? There's no way I'm getting anything other than an integer, right? I'm not gonna get a fraction out of it, but I am gonna have fractions come up, but they should sort of cancel out. So I'm gonna use this 2 to take out the stuff below it, because really, all I really want to do is I want to go for upper triangular form, right? Because remember the determinant of an upper triangular is just the product of the diagonals, right? That's the easiest thing for me to go to. So let me use this 2 to take these out. 1002, 0214. I'm gonna multiply this by -3 to take this animal out. Let's see, -3 plus 1 is -2. And -3 minus 2, so that's -14. And, well, I'm gonna have to multiply this by -5/2, right? Which is unfortunate, but I'll do that. Let's see, that's going to be -5/2. And -5/2 times 4 works out a little bit nicer. That's -10, so it's gonna be -11. And just so I don't have to make my fractions worse, I'm gonna pull a -2 out of the third row. Why not? Feel free to do that. A -2 times -2 is 4. Zero, 2, 1, 4, 0, 0, 1, 7, 0, 0, minus 5 halves, minus 11. Are you okay with it? Yes,
How did you pull a multiple percent of one row?
well, because remember, multiplying any row just multiplies that factor by this, so basically I can pull this out, right? And so in other words, think of it this way. If I multiply this row by 2, well, -2 really, I should get that, agreed? So that means that that determinant should be -2 times this one, so that's what I'm for. Last thing I have to do is row reduction, just take out the 5 halves or -5 halves, and then I'll have an upper triangle, right? This is 4, 1, 0, 0, 2, 0, 2, 1, 4, 0, 0, 1, 7. Multiply this by 5 halves and add 0, 0, 0. 5 halves times 7 is 35 halves, minus 22 halves is 13 halves. So the determinant of this well, we got this 4 hanging around here, which should be 4 times the product of the diagonal elements. 1 times 2 times 1 times 13 halves. Right, 52. It makes it feel good because it should be an inch. Everybody okay? Yes,
So like, what's the determinant tell you? Like, what's that 52 mean?
and then, well, for right now, it just means it's not 0, right? So it means it's invertible. The determinant, so the question might be, you know, what does that number mean? That we're gonna see some subtleties on that. It actually comes up in stuff that's, it has to do with size in a certain sense, so the determinant, actually, here's another kind of neat thing. The determinant of this is 52, that means it's invertible. Anybody want to guess what the determinant of the inverse of this matrix is going to be? Yes. That's pretty close.
1 over determinant.
Well, that's correct. In this case, 1 over 52, right? And of course, that's actually a big fat problem for a matrix of determinant 0, right? So that's a good thing about math is it always kind of, you know, you can always kind of come full circle and check yourself. Okay, any other questions? So yeah, so what the number means right now, the big bifurcation for you all right now is this: determinant 0, not invertible. Determinant not 0, it's got an inverse, right? The subtlety of what that tells you, we'll get more into that a little bit later in the course. So let me make the following note. Given any n by n matrix, we can reduce it to U upper triangular or lower if you like. Via a sequence of row operations. And in fact, not only that, you can do it without multiplying any row by a scalar. In fact, you can do it row replacements and swaps. I did do some scalar multiplication on the previous example, but I didn't have to, right? You can all do this with the sequence, row replacements and swaps. And so. And if you do this, so if you reduce your matrix via a sequence of row replacements and swaps, then the determinant of A is equal to 0 if A is non-invertible. That is, if you row reduction, if you get less than n pivots or n pivot columns, 0, or if you get a row of zeros, or if you get a column of zeros, it'll be 0. Or if not, times the product of pivots in U, where R number of swaps. So if you only use row replacement and swapping, then all you have to do is count your swaps, and once you've got it into echelon form, just take the product of pivots, right? That's all you got to do, which is really kind of cool. So for example, let me just, I mean, this is all silly, but I'll do a quick 2x2 example. Another term high, right? But the point is, if you do a row replacement, so this is equivalent to 3-1. Now multiply this by minus 7/3 and add, kill that, right? So it's going to be minus 7/3 is 4. And I won't even figure out what that is, doesn't matter. When I multiply the product of pivots on the upper triangular, I get 12 minus 7, which is 5. Okay. Any questions? So to kind of come full circle. No. Here. If and only if determinant is not 0. And you've seen this before, haven't you? When we talked about that in the review session, you've seen somewhere the determinant not 0 is used for. Okay, and did you do that differential equation? Oh, okay. And so there, we've now come full circle. If you get any non-zero number, why is this true? Well, if it's invertible, that's true if and only if it's got n pivots, right? And if it's got n pivots, then that means that all those diagonal entries, once you get to echelon form, are not 0. And so you get the determinant, it's not 0. Okay. Any questions? Okay, I'm going to use 2 big theorems and show you some consequences. This first theorem actually shows, and this is really kind of cool, because now you've got another degree of freedom. It's not just the row operations that leave things alone, it's also the column operations. Theorem. Yeah. then if you have any square matrix, the determinant of that matrix and the determinant that's transposed are the same. This is another induction thing. You kind of build a ladder and show it's true for bigger and bigger matrices. So let me just kind of give you. This is certainly true for a 1-by-1 matrix. By the way, this is a stupid question, but I'm not above stupid questions. If you have a 1-by-1 matrix, what's its determinant? One. Well, actually, it's just whatever the entry is itself, right? Oh, think about this. This is just, the matrix is like a number, right? A number is invertible if and only if the number is not what? Zero. So that you come full circle with this, right? So the determinant is just whatever the entry, right? Okay, that was kind of stupid. And what's the transpose of this? Right? How about something with a little more deep to it? Well, suppose I have A, B, C, D. The determinant of this is transpose and somehow this works out to be the same, right? A, B, C. So it works for 2-by-2 as well. Everybody agree with me? This still, I don't think, is painting a very clear picture. So let's look at 3-by-3s and see what happens, because 3-by-3 is the first time that it's a little bit nice. There's and A transpose. I don't have to look at that. You know, you turn the columns into the rows in order. So this is A11, A21, A31. The second column is A12, A22, A32. Third column, A13, A23. This is where it starts to get a little bit more complex, right? Because A11 times this, and now you've got a different number here. What should I do perhaps? What I'm going to do is I'm going to expand this one around first column or first row. I'm going to expand this one around first column, right? Because then I've got the same numbers, right? Because I'm going to have A11 times a smaller determinant, A12 times a smaller determinant, A13. So what do I get for A? What do I get for A? I'm going to get A11. I'm going to get A11 times the determinant. A22, A23, A32, A33 minus A12, A21, A23, A31, A33 plus A3 times the determinant of A1 is A21, A22, A31, A3. That's the mess all the way. Questions? What about the determinant of A transpose? Well, I'm going to expand this about the first column. So it's going to be A11. Determinant of A22, A32. A, 2, 3, A, 3, 3. Minus A, 2, 1. I'm sorry, A, 1, 2. Determinant, A, 2, 1, A, 3, 1. A, 2, 3, A, 3, 3. Plus A, 1, 3, determinant of A, 2, 1, A, 3, 1, A, 2, 2, A, 3, 2, and I look and I don't get a match. Oh dear, please help. Well, it doesn't match. Yes,
With the 2 by 2, it didn't matter if the interior was transposed.
that's right. Where's the relationship between this matrix and this matrix? They're transposed, so they have the same determinant. So even though these matrices look different, they're barfing out the same number, right? Same here, these are transposes. So you get the same thing. How do you do this in general? Put a whole bunch of crap instead of 3, right? And it's the same thing. You expand across the row, you expand across the column, and every smaller submatrix is going to be the transpose of the other, right? And so, again, you build the ladder. It works for 2, it works for 3. You get to work by 4, you expand by the column, you already know it works by 3, now you got it by 4, and so. So that's essentially the gist of why it's true. Anybody, any questions on that? Is that pretty clear why that works out? This is a big important theorem. The determinant of A and the determinant of its transpose, always the same. And here is, here's the map data. So this is the big golden star theorem today. Suppose you have your favorite 2 square matrices. Anybody want to guess what nice property this has? Yeah.
Would it happen to be the determinant of the A times the?
Yes, that's right. And if it weren't, not only would I probably not write that on the board, because it would be wrong, but we probably wouldn't care as much about matrices. Right? This is actually a very important topic. The determinant of a product of 2 matrices is the product of their determinants. This is not clear, I don't think at all, right? But it works. And so let me give you, before I demonstrate why this is true, let me point something out. Suppose A is an invertible matrix, right? And of course, that's P squared. Then if well, then what is find the determinant of A inverse, right? I mean, I haven't even told you what A is, now I'm asking you to determine the A inverse. Well, what does it mean? What does it mean for a matrix to be inverse? It means that when I take A and I multiply it by A inverse, what do I get? You get the identity matrix, and I'm digging on the identity matrix because it's upper triangular. In fact, it's diagonal. Take the determinant of both sides. Which should be the determinant of I n. What's the determinant of the identity matrix? Yeah,
One.
one, it's just the product of all the diagonal entries, because it's diagonal, and all the diagonal entries are ones. So that means the determinant of A inverse is one, and we can determine of A. And again, math takes care of you. This is a dead giveaway that you've got serious trouble trying to invert a matrix if it's determinant into anything, or if it's determinant into zero. Okay, so I want to give you an idea of why that determinant product is true. So y is determinant A B equal determinant of A. Well, number one, if A or B is singular. So, yes. This is something that we have from earlier. So if A can't be inverted or if B can't be inverted, when you multiply A and B, it can't be inverted, right? So if A or B is singular, that means they're determined to zero. So what you get in this case is zero is one of these two factors has to be zero and it works, right? That's not the interesting case anymore. So this works. If not, if A and B, well, let's actually go now. A is not singular. Then A can be reduced to the identity matrix by a sequence of row operations. Everybody okay with that? That's one of our equivalent ways to think you can make this be a new variable. You have to be able to do a sequence of row operations, the identity out of it, right? So that means if you take A and then row operation one, row operation two, if you do this enough times, you get the identity matrix. Well, actually, and I'm going to go the other way on this, I guess. Or you can invert the row operations and get the matrix and the identity here. So, how does this help us out? Well, so A is the product of these, and if A is a matrix n by n, and E is represents an elementary row operation, and determinant of EA is determinant of E. This is actually in essence what we've done earlier. This is just all the cases are row operations. It was the first theorem today. One row operation is adding a multiple of a row to another row, right? Those matrices are always upper or lower triangular and they have ones on the diagonal, right? And so determinant of this is unchanged and that's determinant one, so that works. Swapping two rows, if you do the matrix that swaps two rows is just swapping two rows on the identity matrix, that has determinant -1, that has determinant -8, so it works out. And multiplying a row by a scalar basically multiplies the determinant by that scalar, and that's basically the diagonal matrix with K and the appropriate entry. So since this works for the elementary matrices, if you look at the determinant of AB, you can rewrite A as this product of elementary operations. That messes B. Now by this operation, I can pull these E's out one at a time. By this operation again, I can put all the E's back together. So I get determinant of A, that's what this is. Determinant. And that's it. Any questions on that? Okay, so I've got you up under the hood with all this stuff. Remember this is about the transpose, the change, the determinant, the products, and big one, practice this stuff, and I will see you on Wednesday. Oh, folks, also, my meetings actually start at 1 today, probably for the next 10 weeks. So if you want to meet me, after 1, you're going to need to copy and start to set things up. I'll be out of my office at 1.